posted, and for some reason it didn't post, and I think it had to do with a bunch of updates my computer got. But then it posted, and I realized it posted late, so did everybody get the email I sent?
Yes, sir.
Okay. And I apologize for, did you have any questions about it? I don't think you did, at least one. No? With the radar, y'all did it. We may not have had time. I wanted to do at least one of these things. How many have tried it at least? Anybody? Nobody? You did it? Do you have it with you? Go ahead. Do you have a question?
Can you do 7.5.4?
Yeah, can you give me the specifics?
It said antenna on an aircraft is being used as an ECM. Antenna has a gain of 12 decibels in direction of transmission.
All right, hold on for 1 second. Just try. So at the aircraft, the gain is what?
12 decibels.
12 dB, go ahead.
And that's in the direction of transmission, and transmitted power is 5 kilowatts. It says determine E field intensity in the vicinity of enemy radar, which is 2 miles away.
All right, this is a straightforward problem. They give you the gain, the power transmitted, and the range. And they say it's a range of 2 miles. And this is the kind of problem, they're just, if you know your stuff, it's real quick. If you don't, there's a whole lot of confusion. So I'm 2 miles away, I know the power transmitted, and I know the gain of the antenna. That's all you need for the E field. First, what I'm going to do is find the average power density right here, okay? That's the first thing, because once I have that, if you have power density, you have E field. You all understand that, class? If you have the power density, necessarily you have the E field, because the average power density is equal to 1/2 magnitude of the E field squared over 8 if this is the atmosphere. Everybody with me?
What is your notation for gain?
Gain in dB. I think I put notes in there. Gain in dB is 10 log gain linear. So gain, first of all, is equal to the efficiency of the antenna times the directivity of the antenna. Now, if the efficiency is not given and gain's given, it's better, because technically speaking, average power density is equal to the gain, which would be efficiency times directivity. It's the gain of the antenna, in this case is the transmitter, times the power transmitted over 4 pi r squared. Without the gain, this is the isotropic power density that would be present. If you just take the total power and divide it by the surface of a sphere at a distance r away, there's no focusing. The gain focuses it. With me on that? That would be the average power density. The trick with this one is it's in dB. Most of the time, when you're dealing with any quantities that have orders of magnitude of difference, they go to a logarithmic scale or dB. And for power, when they talk about power in dB, it's 10 times the log, and this is a base 10 log, not a base E log, of the actual power. And if it's gain in dB, because gain is a quantity related to power, it's 10 times the log of the gain that's linear. Y'all with me, class? So the gain is given as 12 dB. Now I'm going to work through this, and I want to work through it in a way that hopefully answers any possible questions you have. The first thing I need to get is this gain. That's a linear gain. Y'all follow me? Gain in dB is not linear. That's logarithmic. So I come over here, and I say that gain in dB, that's what I have, is equal to 10 times the log of the gain that's linear. That's what I want. So I have 12 dB over here.
I'm a little confused about, so when you say that is it linear for that equation, if the gain is linear, you use that equation, so when it's not linear, you're using the log?
All right, let me try to explain something. Because gain has orders of magnitude of difference. In the linear scale, by linear, I just mean it's scalar. It's a proportional gain. If a gain can be like 1.64, it can be 10, it can be 100, it can be 1,000. That's how much better the actual focusing power is of the power density. But when we do logarithmic work, now we could do this in log, and I do that in the radar class. I can take a log of this and a log of all this quantity. I don't want to confuse you with that. I'm just going to show you how to take the gain in logarithmic terms and turn it into a gain in linear. The gain in linear does not have dB. That's the key. The linear gain is unitless. When you see dB, you know you've got to convert it to the actual linear gain if you want to go back to the actual standard radar range equation, which is right there. So do you follow me on this one?
Yes, sir, that makes sense.
This is, how many have seen this before? All right, this is standard dB, right? And if you're an engineer, you're going to use dB probably all the time. All the time. So here, I get 1.2 is equal to the log, and that's a base 10 log. I'm saying that for a reason. Does anybody want to know I'm saying base 10 log? Anybody?
Might be natural log, base E.
Yeah, MATLAB log function is log base E. You have to put log 10 in MATLAB if you want a base 10 log. Y'all understand that? Now that is a subtlety that gets people all the time in MATLAB. How many use MATLAB here? Everybody's supposed to. I try not to give you too many MATLAB assignments. Octave, let me just put this out here. You're going to find out, here's what the real world's like. All the prototyping, that means the first set of code developed that's going to do something, anything complicated, is done in either Octave because it's free, Python because it's free, or if it's complicated and they got money, MATLAB. MATLAB's the best. It's very, very quick. They have cajillion toolboxes and you don't have to worry about an error, but it is pricey. If you don't like MATLAB, start liking MATLAB. You're going to use it, chances are, unless you're just a salesman or you're doing something where you're doing chemical processes all the time. MATLAB is inherent to everything you do as an engineer, just about. I hate to say this, but Python nowadays is too, and so is Octave. Because how many know what Octave is? It's, I call it the free version of MATLAB. It doesn't have quite the versatilities. There's some very subtle differences. And it's not quite as nice in some ways, but Octave is free and I use it all the time. MATLAB isn't. How many know what Python is? In the real world, you will be using Python. What's the real power of Python? Well, there's a couple. What's the, besides being free, and there's cajillions of code. Anybody? Unformatted. You can go ahead and you can pull in data. You can cull data without any formatting. And people like Dr. New, stuff like this, anybody that does big data stuff, that does data mining, or they're trying to design stuff where they're pulling in data sets from everywhere with all sorts of different formats, that does it. In MATLAB, you have to do all sorts of formatting. I'm just telling you that. And that's the nice thing about Python. I don't use Python that much, but I'll tell you my grad student does, so it's forcing me to learn Python more and more every day. They're so similar though, honestly. Anyway, back to this. Yeah.
So, what P average equation do we use? Can we pick the one we use, or do we have?
All right, when I say P average here, I'm talking about the average power density, like you talk about average power in a power world, all right? There's peak power. We don't talk about peak power. Not yet. Y'all with me on that? This is average power when the transmitter is transmitting. Okay? That's what I mean. You all follow me? I mean, you get VRMS, IRMS, multiplied quantities, you get average power, right? That's what I'm talking about here. If it was volts per meter RMS and E field, or volts per meter RMS and amps per meter H field, then you'd get this. But this is the average power. This is the thing you worry about in radar. So, back to this. Y'all see what I'm doing here? Now remember, that's log base 10. Therefore, if I wanted G, I would take 10 to the power 1.2 would be G. Y'all agree with that? Right? I don't know what that is. If somebody can give it to me, it'd be great. That means the average power density I get is going to be that. 10 to the 1.2 times 5 kW, or 5,000 watts, divided by 4 pi. And now you've got to turn a mile into meters. All right, now I wouldn't expect you to know that. The way I do it, and it's archaic, 5,280 feet in a mile, so I multiply 2 miles by that, then I know 0.39 I'm sorry, I'd multiply that quantity by 0.39 to get it into yards, and then I do the conversion from yards to meters. But I'm just telling you, I would not expect you to know that. Can anybody just give that to me in meters? Go ahead.
3,219.
3,200?
3,219.
All right, 3,219 meters, and you gotta square it. Now, this is gonna be the average power density. Can anybody give that to me? We'll compare the answer that we get. It's gonna be the same.
I got 608.5 times 10 to the negative 6.
And that would be watts per meter squared, right? So it's 608, it's quite a bit, actually. You all with me, class? If that's right, okay? I'm hoping it is. So now to get the E field, what do? We take that power density, we have 608.5 times 10 to the minus 6, and then we multiply it by 2, right? And then by 8 and out, what's 8 and out, everyone? 125, right? And then I have to take the square root of the whole thing to get the E field. What do we get for the E field magnitude? Anyway. Y'all agree with this, by the way? It's not hard to see, and I'm sorry if I'm going a little fast. I've got things on my mind I want to do. Anybody? Most of you know this. It's just reinforcing what you read. Now, the slick thing is the only thing you have to do is do the gain, right? Gain conversion, and then miles to meters. That's it. And I wouldn't be expecting you to know. Go ahead.
677 times 10 to the negative 3.
677 times what?
10 to the negative 3.
10 to the minus 3, and that would be volts per meter, right? If we wanted the H field, how would you get it? Is that right, by the way, class?
Yes.
How would we get the H field?
Divided by 125.
Divided by 125,
Yeah.
right? Everybody? We got power density, E field, H field, game over. We got everything we need, right? What else is there anything else in the problem?
No, and I had it up, I think I just typed it in the calculator wrong, didn't it?
So that happens too. That happens to me late at night if I'm not wearing my glasses.
Well, you said we shouldn't expect to know how to do meters to miles.
I would always give you a conversion.
Okay.
I don't expect you to know the conversions from centimeters to inches. Wentworth might, but I don't. And go for Dr. New might. But I'm going to level with you. That kind of stuff is something you'll get to know when you have to do it a lot. It becomes second nature. If you're not, I'll be honest with you nowadays. Like it used to be, the English units were a big deal. I mean, we still use miles, right? More and more, in just about all the stuff in the military, he's in the military, so he can speak to this. More and more, everything's going to kilometers to go into, kilograms, second, all the standard MKS or System International. They're moving, and the reason is because there's seamless transition. Watts is watts is watts. You don't have to go from horsepower to watts or from some other quantity to watts. There's no conversion factors. And that's what irritates me when they do miles and yards and all that stuff, because there's all these little factors that can play a role in getting you the wrong answer. How many had thermo here? Anybody? Do y'all remember steam tables? God, I hated those. That's the most stupid waste of time, extrapolating tables that are in English units. I'm sorry I said that. Don't strike that from the records.
I'll pull it.
Anyway, any other questions about this one? Let's do another one though.
Can you do 8.1.4?
You're gonna have to give me the,
Alright, a wire carrying a 1 milliamp current.
wait, not that one, the last one with the radar. That's the image one. I'll do that, all right, but I wanna do the last.
Target received power.
Yeah, let me erase this, I wanna get it, and I really appreciate you helping me here. I'm so sorry that went out late. Did anybody else get a ton of updates? I have two Lenovo computers, and they had one round of updates, then after you're done with the first round, which took quite a while, they had a second round. Maybe it's just Auburn's doing updates, I don't know. But anyway, I had a whole bunch of updates, come and just lock the computer up, and I thought it was gonna take care of it. Go ahead with that one.
Alright.
What's the number again?
This is just number one,
8.1?
or no, it's just one.
Oh, okay, that one, yeah, I like this one. Go ahead.
It says, using equation 2.8, which we don't know what that is, determine the single pulse received power level from a target for a radar system having the following characteristics.
All right, now that equation is the radar range equation. Go ahead.
It says transmitter is 100 kilowatt peak,
All right. Peak.
frequency is 9.4 gigahertz. The antenna gain is 32 decibels. The target range, the target RCS is 0 dBSM. And then the target range is 50 kilometers.
Does everybody have a feel for how far 50 kilometers is?
Long way.
What is it, 10K is about 6.6 miles, right? Isn't that right? So 100K is 60, right? 50 miles, it's about 30 miles, isn't it, class? I'm just trying to make sure you get an idea in your head of what we're talking about. That's a long way away, is what I'm really trying to say. I mean,
It wouldn't make sense.
a nautical radar at 50 miles, yes, a military nautical radar would work. A regular, does anybody have a radar on your boat or on? All right, 50 miles is a long way to see anything. I don't care if it's a boat, ship. Outside of a mountain range of the Statue of Liberty, it's very hard to see anything. So I'm just making sure you understand, this would be an aircraft radar, typically. All right, so when we have 0 dBm, the first thing we want to make sure is we get everything, yes, sir.
Is that gigahertz or is that 9.46?
It's gigahertz,
Okay.
10 to the 9th hertz. All right? So the first thing I always do, and it would be smart to do this until you start working with dB equations, is turn everything, and I call it the linear domain. Get rid of the dB is what I'm saying. This is in square meters. Now, meters squared is a term that will be used with the power in the radar range equation. Again, the radar range equation I'll put up here, P received is equal to transmitted power over 4 pi r squared. As a matter of fact, let me just put the regular radar range equation in the form that you're going to see it over and over again. There'll be 4 pi here, but it'll be to the 3rd power. R will be to the 4th power because the signal goes out, falls off as 1 over r squared. Then the reflected signal falls off as 1 over r squared, so it's r to the 4th. Then it's going to be times the actual sigma, which is the target RCS, times gain of the transmitter, gain of the receiver, and there'll be a lambda squared there. The reason that lambda squared pops into the equation is you know the effective aperture or aperture of the actual target there is lambda squared over the size, electrical size of this antenna is lambda squared over 4 pi times the gain of the transmitter. Do y'all remember this? It gives you an area. So this is in dB. I'm going to bring it into what I call the linear, or getting rid of dB. So I know 0 is equal to 10 times log of sigma. Y'all follow me on what I'm doing? Just so you'll know the steps. You with me? Normally it's just gain, the word sigma in dB is equal to what? 10 times the log of sigma normal. Y'all with me? Want to make sure we find sigma normal. So what do? Divide 0 by 10, you get 0, right? And then I take everything to the 10th power, so 10 to the 0 is sigma, or 1 meter squared. That's how you get it. And 0 dB is sort of a standard target size that's used for scaling or calibrating, things like this. And what they really do is they get an aluminum covered or a metal sphere of a radius, a diameter, radius of 1 meter, so 2 meters diameter. And they use that to calibrate real radars. And that comes later. But that way they know what they're getting at a given range, and they know exactly how to adjust things. All right, so now they have that. Next thing we have to do is get the gain from dB to linear, correct, class? Everybody with me here? So how do I do it? Anyone?
32 equals 10 log.
Remember, are all your calculators LOG is base 10 on your calc? I'm hoping that's true. R times gain, right? You should have an ln function. That's the way I used to distinguish the two when I was in school. But MATLAB is MATLAB. Okay, so that means I have to take 32 by 10 to 3.2, and 10 to the 3.2 power is the gain. Just a little over 1,000. Do you agree, class? Next, we gotta get wavelength. So what's wavelength? C over F, right? That's 3 times 10 to the 8th meters per second divided by 9.4 times 10 to the 9th. So it's 3 over 9.4 times 10 to the minus 1. I don't know exactly what that is. It looks like
0.0319.
Thank you. And that would be meters. After that, I think we got everything, and the assumption is gain of the transmitter is equal to gain of the receiver.
Is that true for all of the radars?
No. Monostatic radars usually, unless they're expensive, they use the same antenna to send. So they send, all right, then they listen for reflections, and then when the ambiguous range passes, that length of time, then they send again and listen. But with bistatic radars, and there's a story behind this, in the first Gulf War, back in '91, I think it was, the British could see our stealth fighters because they had bistatic radar. It's not cheap and it's not easy to make because the stealth fighter is not invisible. It just reflects all the energy away from the transmitter. So the AAA stuff that they had, that's basically monostatic, they couldn't see a thing. They were just shooting in the sky. Bistatic radars are much more expensive, and it's usually not one antenna that you hit, and then they'll have an array of antennas on the ground that have one transmitter, and they'll look at all the reflected energy from what the signals they sent, and then they basically do an inversion problem to locate the target. And it's very, very hard for stealth to work against that. However, there are tricks to defeating that, and one is, I'm saying this because some of you are going to end up working with military. Low observables, when you fly at the ground level, you know what a cruise missile is? Almost impossible to pick that out, almost impossible. So they'll fly very low with a small thermal signature and basically pop up when we need to. That's the truth, and those are very tough to find. All right, so now we got everything, don't we? What did they ask for? The receive power?
Yes.
All right, so now we just take this equation, which I was about to put here, the radar range equation, and I've got it right here, and I'll just put it on. P receive, this will be peak. If they say that transmitted power is peak, then this is going to be peak. This transmitted power, which is 10 to the 5th watts, right? Then it's going to be times sigma, which is 1, that's a nice number, times gain of transmitter, gain of receiver, so it's 10 to the 3.2 times 10 to the 3.2. Usually I just combine those and make it 10 to the what, 6.4, but I'm breaking them out there so you understand. Gain appears twice. Then after that I have to put lambda squared. That's 0. Remember, this is a squared quantity. Then this is going to be divided by 4 pi cubed r to the 4th, and that will be the received power density. Now, would anybody, can you give that to me? And R, by the way, and this is 50K, so I'll put 50.
It's 2 point, are you ready for it?
Go ahead.
It's 2.061 times 10 to the minus 14 watts.
All right, let me make a comment. That's not much. That's not much at all. As a matter of fact, I can tell you right now, that kind of power density for almost every radar, unless you got a cryo-cooled radar or something like that, that's in the noise. Now the way they can pull signal out of noise, because what they do is coherent pulses, processing. They take a timed picture of the entire received signal, and then they hash it up into the actual, you might say, 1 PRI long. And they superimpose all those things using digital signal processing, and the noise does not add. It will, it's wide sense stationary noise, but the signal will, and they'll be able to see the signal that way. That's later, that's more signal processing, that's really cool. Because you can see that far away. The problem is you can't see instantly. It takes a while before enough information happens that you can get it out. Have you ever noticed that a police radar, I don't know if you've ever seen this kind of stuff, but it doesn't give that speed instantly. It has to do coherent processing. It has to collect data on you for a while before the signal over the noise becomes apparent and they can get your velocity. I'm being honest with you about this. It's not as easy as it looks. Now, it's different with a laser, because that's just time. Go ahead.
I'm not sure if you explained this earlier, but so the gain received versus gain transmit are the same for this problem. Is that standard, or is that just from problem to
For
problem?
most, I'd say commercially available radars, it's true.
Okay.
Military radars, you can't make that assumption.
Okay.
Military, it's totally different ballgame. And I should say this because I don't know. Navigational radars and weather radars, I believe it is true, but anymore now with the Doppler stuff that they're doing, I'm not absolutely certain. I can't say that confidently. But navigational radars like in Atlanta Airport, as far as I know, they're still tower controlled monostatic. They have a revolving parabolic dish and stuff like this. But I don't know that 100%, because bistatic is useful at times if you got a lot of mountain ranges and stuff and they've got radars all over the place where they want to make sure they don't have some non-compliant vehicle coming in and just, crash your airspace, because that, you don't realize how much trouble it causes just one plane to get inside what's called the actual takeoff pass and stuff, because you're supposed to be behind, as far as behind one of those big planes, you shouldn't be there any sooner than 2 minutes later. And if you have any kind of wake vortex and you fly a small aircraft in there, not only they may crash, they may run into another plane, even though they don't think they can. So that's the big deal. They would like to know where everything is. Is that correct? Okay, yeah.
So doesn't the two problems we just did pretty much cover all the radar equations we need?
Doesn't what?
Don't the last two problems we did pretty much cover all the radar equations we need?
Well, they're in a very general sense, yes.
There's a second part of that question.
Yeah, go ahead.
It says, the target approaching the radar, that same radar, the velocity is 2,000 meters a
This is-
second.
this is good.
Determine the Doppler shift.
All right, so now, this is the velocity in this direction is 2,000 meters per second. And now I want the Doppler frequency. So what's that? Do you remember?
2V over lambda.
That's right. It's 2 times the velocity, that's the radial component, over lambda. Now we can check this. I think I gave you the answer for this one. So this is a straight formula that we developed, so this is going to be equal to 2 times V, which is 2,000, divided by lambda, which is 0.0319. And I forgot exactly what that is, but I know
12.5
12.5.
kilohertz.
Now this would be the shift that you would add to this to see if you have a spectral analyzer, which is almost none. And the only way they figure out that there is a Doppler shift, they have to take a sine and cosine waveform at this frequency, and they multiply it by the received signal, and then they low pass filter it, and then they can see the actual shift. But that's more with more advanced radars. You all know how to do sum and difference when you multiply by cosine and sine? Right?
That's what I see.
If you have a yeah,
It's 125 kilohertz.
125 kilohertz?
But it's wrong on here as well.
Yeah.
That's the solutions are wrong. It's 125?
Mhm.
Okay. Is that right? 125 class?
Yeah.
Okay. But that's the frequency that would be added to the transmitter frequency that would be the apparent frequency of the received signal.
Okay. So you're saying adding those two together right there would be the actual receive signal?
The actual receive frequency you would get would be 9.4 gigahertz
Yes, sir.
plus this.
Yes,
Now,
sir.
think about this. If you've ever been to a car race or even stood at the highway, when cars approach, you hear, and when they pass by, that's a Doppler shift. All right? The rev on the engine hasn't changed, but what you're hearing has, because as it moves away, the speed of sound slows down the transit. You might say it slows it down, and so the apparent wavelength is longer. When it's coming at you, it compresses it. That's the reason for it, if you want kind of a physical insight into what's going on. But honestly, I mean, speed of sound is always a constant. The engine rev's a constant. The problem is the distance is changing, so the apparent, you might say, wavelength gets crushed. And that's one way of thinking about it. All right, another one?
So a quick question about that, I guess, then, since 125K in comparison to 9.4 gigahertz is basically nothing, so you're
Right.
saying they basically, the receiver would still receive it at 9.4
What you would
gigahertz.
do, your receiver would be the same transmit antenna, because there's such a small, you would receive that signal with the same antenna. Then when you get that, here's what usually happens. They mix it with a very stable local oscillator, both a sine and a cosine wave. Now, what happens is that whenever you take a sine or a cosine at the same frequency of a received signal, regardless, as long as there's cosine or sine variation, regardless of the phase of that, you're going to get two frequencies, and what we do is something that's in phase and quadrature processing. Now, I'm not gonna go there now, but we will be able to determine the actual low frequency signal once we stick the results of that through a low pass filter. Y'all know when you take, if you have a sine of omega naught t, and then another sine of omega naught t, and you multiply them, you get so you get sine, you get 1/2 plus sine of 2 omega naught t plus the phase difference of the second one over 2, right? So if you low pass filter, you get the 1/2, right? But if there's a small frequency difference in the actual signal itself, that'll appear in that 1/2 portion. And I can show you the math on that later, but that's what really happens. Another question?
A wire carrying a 1 milliamp current.
I'll do that word for you. This is the imaging thing.
That was all the radar was.
Well, this is antennas too. I mean, you can't separate. It's not just radar, it's not just antennas, it's all the things lumped together. This is a good one. I had somebody ask me questions in my office. What did you about the radar? Who was it? The kid? Wasn't it you?
I did antennas, not radar.
Huh? Not this one, but you asked me about the radiation resistance. Remember that? Yeah, okay. Go ahead. We got a wire above a ground plate, don't we?
Yes.
And the wire is how long?
1 meter.
All right, that's a nice distance.
And
Yeah.
it's 1 centimeter above
1 centimeter above. Go ahead.
and it says it's got a current of 1 milliamp at 100 megahertz. And it says determine the E field 3 meters above the ground plane.
This is a standard EMC test, compliance test. So they want the E field here, and they want it at a range R equal 3 meters. So just imagine this. By the way, this problem right here is actually something you could pretty much replicate in a lab. This isn't hard to do. You got a little wire. We're going to assume it's a straight wire. It's above a plane. I've got the frequency at 100 megahertz, right? 100 megahertz is 3 meters, right? So this is 1/3 of a meter. We'll treat it as a short dipole, even though it's a bit of, we're being very, you might say, relaxed with our, thing has to be at less than 1/10 of a wavelength to do this. It's 1/3 of a meter. In the real world, it would still be real close to a short dipole. Even a half-wave dipole's radiation effects are pretty much that of a short dipole, if you think about it. If you think about the 1.64 gain versus 1.5, just about the same. All right, for the max gain. But what we want to do is imaging on this to get the electric field up there. Do y'all follow me? Now this is a cool one because this forces you to do standard image theory. So the way you do image theory is what? I'm going to start with my first current, and I know I here was 1 milliamp, and I'm putting it that direction, right? Now the ground plane is 1 centimeter below it, right? Y'all with me on this one? Now, which way does the current image below it? Opposite direction, same depth, right, as above. So there's going to be a fictitious, but real, but the effects will be real. Current here, I equals 1 milliamp in the opposite direction. Y'all follow me? Now the actual range here, R, was equal to 3 meters, right? If they want the electric field that would be measured up there, all right? So what is the electric field from a short dipole? It would be perpendicular to this, right? Right, class? So what is the electric field in general perpendicular to a short dipole? Well, the E field would be J eta beta over 4 pi, right? R times L, e to the minus j beta r, this quantity will be important, times the sine of theta in the a theta direction. Y'all follow me? I'm just putting the formula down that you've seen over and over again. Correct, class? Okay, now I'm going to make some adjustments to it. First, y'all agree the angle is 90 degrees. Everybody? If it's 90, the sine of 90 is 1, correct? So just erase it. Next thing I'm going to do is this. I've got eta beta, right? Over 4 pi times L over R. L is 1, isn't it, class? If L is 1, get rid of it. Right? Now y'all agree with me so far? And I'm just getting the form that will work here. Next, I take eta, I'm going to leave the j in here. Eta is 120 pi, right? Times beta, well beta is 2 pi over lambda, isn't it, class? So I've got eta times beta over 4 pi. Oh, I forgot one thing, I, right there, right? Over 4 pi times r, and r is going to be 3, but you know, 3 plus a centimeter, 3 minus a centimeter is about 3. Magnitude is not going to change much. Do y'all give me that, class? It's not. It'll change with that phase though in a second, but this is the first part right here. I know I still have this e to the minus j beta r term that I'm going to get to in 1 second. And I know it's in the a theta direction, it's times I as well. What I wanted to do is simplify this as much as possible. Y'all agree with me so far? Now this is just the way I'm doing it, simplifying. I know the wavelength is 1, don't I? If I got a frequency of 300 megahertz, that's 3 times 10 to the 8th, then I can see that lambda is c over f, or this is going to be, actually it's not 1. 3 times, is it 300 or 100 megahertz?
100.
It's 100.
Okay, so this is 3 times 10 to the 8th over 10 to the 8th, or this is 3 meters. Sorry. So if it's 3 meters, then this becomes 3 here as well. And now I'm just going to try to simplify this equation. So I got 2 pi and 4 pi. I'll make that a 2 down here. And then I got 2 into 120 is 60. Pi remains. And I got 3 into 60 right there is going to be 20. 20 divided by 3 I'm going to leave alone. And so this is going to be J 20 by 20 pi by 3 times I, right there. Y'all agree with that? All right, now here's the next part, and I gotta be careful about this. When I look at the E fields from these two, I'm gonna start with this one. I'm gonna call this 1 and this 2 as far as the source points. When I get the E field out here, I know the actual range from this one, R, is gonna be R naught minus 1 centimeter, right? And the range from this one is gonna be R naught plus 1 centimeter. I'm just saying that if you're taking the reference as the ground plane, those would be the radial distance differences, right? You all follow me on this? With me? Okay? With me? This would be the range from this one up to 3 meters. This would be the range from this one up to 3 meters, if 3 meters is measured from the ground. So now, when I take this and get the E field total from those at 3 meters, from the first one, I'll always have this J 20 pi over 3 times I. Times I. All right, now, for the first one, we'll take that sense positive. So the E field from this one will be sense positive. It's gonna be a plus E to the minus J beta, and then it's gonna be R minus 1 centimeter. And here's what I'll do. I'll call the delta R equal to 1 centimeter to make this easier. So it's gonna be R minus delta R. And then, that would be, y'all follow me, this would be the E field just from the first dipole right here at this point, if there was nothing else. Y'all see that? All right, now the second one's in the opposite direction, right? So the E field from the second one would have a negative sense. Do you agree with this, class? The I could be negative if you want some help with the instinct. So this is going to be minus E to the minus J, and this is going to be beta. Here it's going to be R plus delta R. Y'all follow me? The only thing I've done here is this distance changes. The 1 over R is the same for both of them. Everybody follow me on that? All right, now, the next step, let me do it right here when I look at E total. What I can do is I can gather an E to the minus J beta R out of this term and this term and pull that out in front. Do y'all see that? I'm going to take all that other stuff. I'll take the J 20 pi over 3 out front. I'm going to take I2. That's just going to be, what is it, 1 milliamp. And then I can take the E to the minus J beta R out front. R there is 3 meters, but don't worry about that. And then I have this. I have E to the plus J beta delta R minus E to the minus J beta delta R, don't I? I'm going to see what I'm going to do next. Anybody? There's something that should be coming to mind in a lot of your heads. What am I thinking of anyway?
The signs cancel.
That's right, that's a sine. Sure. I know what? Sine of theta, you don't have to do this, is what? E to the J theta minus E to the minus J theta over 2J. Isn't it, class? Do y'all remember that? So if I multiply sine by 2J, I get that. And what is that theta then? It's beta delta R, right? Delta R is 1 centimeter. Y'all see that? Take a good look. Do you agree with me? I want to make sure everybody sees this. Do you see it? This right here, 2J sine theta is E to the J theta minus E to the minus J theta, right? All right, I'm going to stick that in there. That means my E total is going to be equal to J times 20 pi over 3 times I times E to the minus J beta R. You can forget about that term and that J, those are phases. And then this becomes J times 2 times the sine of beta delta R. And it would be in radians. Y'all with me? Here's the fun part about this. Now that's going to be the total E field. But beta delta R, for our problem, beta is 2 pi over lambda, isn't it? And delta R is just delta R. So it's 2 pi times delta R, which is 1 centimeter, or really 10 to the minus 2 meters, over lambda, and lambda is 3, correct? Now this would be in radians. Do y'all see this, class? That's a small number, isn't it? I got 10 to the minus 2 over 3. So it's 1 over 300 times 2 pi. Do you know the sine of a small number is about the small number, class? Sine of x is about x when x is small. How many know that? So what I can do is take this whole thing, and I can get rid of the sine and just put this in. You tell me if this isn't the right answer. And the only thing you do is put that in. Put in 2 pi over lambda, which is 3, times 10 to the minus 2. Here you're going to make, you can forget about j because the only thing they care about is magnitude. J is a phase term, e to the minus j beta r is a phase term. The I is 1 milliamp, so that's 10 to the minus third here. And forget about that j. So what do you get for the answer? Does anybody have a calculator? You don't mind doing this? It's 20 pi over 3 times 10 to the minus third times 2. Times 2 pi over 3 times 10 to the minus 2. And we'll see if we get the right answer. I bet you we do. But y'all, you see what I've done there? It's just using imaging. What did you get?
I just had a question real quick. Just to reiterate, you dropped everything with a J in it because that's all polar stuff and we're looking for the
All
magnitude.
phase, right? If you don't care about the phase, they give you magnitude only. In the real world, that's what you care about. What did you get for this one, guys? I'm curious.
I got 877 times 10 to the negative 6.
877 times 10 to the minus 6 volts per meter. What's the answer? I'm curious.
That's what I got.
What's the
Eight.
answer? Is that it?
Yep.
Okay, we got it. Now, you can do the sign. It has to be in radians because beta would be radians per meter, right? But you get the same exact value because the sign is small. That's how you do that problem. The real trick is just put an image below there, the same distance, then add the total field. That's it. I wouldn't ask you to do something like that at an off angle, like at 45 degrees, because then it gets a little more tricky. Right? But if it's straight up above it, it's easy to see. Yes, sir.
Since we have j in this equation, if we want to calculate raising sign, do we have to change it to radians, not degrees?
Well, the J has nothing to do with radians or degrees. It's an imaginary term. So and it has to do with phase. J is simply 1 at an angle of 90 degrees, or it's 1 at an angle of pi over 2 radians, or it can be e to the j pi over 2 radians, or e to the j 90 degrees. J doesn't have anything to do with degrees or radians itself. It just means it's an imaginary quantity. That's all. And I'm out of time, and I got to test on the next slide. So for the exam on Friday, it's comprehensive, but it'll cover all. If I was you, look at your quizzes, look at the material and homework. Right? I'm not going to cover arrays, obviously. Right? But it'll cover everything we did up to, through today's lecture. Yeah.
Can we expect a formula sheet?
For halfway dipole, yes, I would give you that formula. I'd give you, you're not going to get a Smith chart on this one, but if I would give you like the input impedance to a transmission line, you know, that Z naught times.
Plus minus the ZL.
But and for halfway dipole, I'll give you the actual gain formula versus angle, because it's got the cosine pi over 2 cosine theta over sine theta business. Halfway, for short dipoles, you have to know it. Any kind of loop antennas, you don't need to know radiation resistance. You just have to know the gain of a loop antenna is a small loop antenna. And you have to know the formulas related to dipoles. And that's really, I mean, I don't give formula sheets per se, but if it gets a little hairy, I will give it.
So if you haven't given it to us on a quiz, basically expect to be able to.
That's right.
remember it.
Anything on the quiz is fair game. More likely, it's going to be game. All right.